All right, let's get into it. Today, we're pulling back the curtain on some seriously clever tech that you use every single day, probably without even thinking about it. We're talking tree-based string algorithms.
So, you ever stop and think about how your phone's autocomplete is just freakishly fast? Like it suggests the perfect word before you're even done typing. Or how a spell checker can blaze through an entire document in the blink of an eye? It's kind of wild, right? How in the world can a program search millions, literally millions of words, almost instantly?
Well, the secret sauce here isn't magic, though it kind of feels like it. It's actually a super elegant and ridiculously efficient data structure called a trie. And that's what we're here to do today. We're going to break down exactly how it works and, more importantly, why it's such a powerhouse.
Okay, so first things first, what even is a trie? To really get why it's so special, we've got to start with its other name, which honestly gives the whole game away, the prefix tree.
So yeah, a tree, or like we just said, a prefix tree, is this special kind of tree data structure. But here's the key difference. Instead of storing numbers like a lot of trees you might know, this one is built from the ground up just for strings. You can think of it like this. Every single path you can take from the very top, the root, down through the branches literally spells out a word, one character at a time.
You know, the best way to really wrap your head around this is to think of it like a souped-up phone book. But instead of just flipping to the S section to find Smith, you're following a specific path. You take the S branch, and from there you take the M branch, then I, and so on. And what's really cool is this means words that share a prefix, say T and 10. They actually share the exact same path in the tree for T and E. They only split off at the very end.
All right, let's actually build one. It's the easiest way to see it in action. Let's say we want to insert the word T. We always start at the very top, at the root. Now we ask, is there a path for the letter T? Since this is our very first word, nope, there isn't. So we just create it.
Easy enough, right? So now we're at the T node. We do the same thing again. We look for a branch for E. And again, it's not there yet. So boom, we add it. You can see what's happening here. We're literally just spelling out the word, creating a new node for every single character.
And last but not least, we add the final character A. But this is where the magic happens. This is the crucial bit. How does the tree know that TEA is a real, complete word, but TE is just, well, a prefix? We have to mark this final A node somehow. Usually it's a special flag in the code, but for now, this little check mark does the trick. It shouts, hey, a word ends here.
And once you have that structure set up, everything else just clicks into place. It's so intuitive. Want to search for T? You just retrace the exact steps we just took. Want to check if any words in our dictionary start with T? Simple. You just walk the path down to the E node. It really is all about just following the path of characters.
Now, this simple idea, just following a path, is what gives the tree its actual superpower. And it all boils down to one thing. It's mind-blowing efficiency.
And that superpower has a name, Big O of M. So, what does O of M actually mean in plain English? It means that the time it takes to do anything, search, insert, delete, it only depends on the length of the word itself. We call that length M. It does not depend on how many words are already in the trie. Think about that for a second. Whether your dictionary has 10 words or 10 million words, finding TEA still only takes those same 3 steps. That's a game changer.
And this isn't just a best-case scenario. The performance is incredibly consistent. If you look at this table, you'll see that for search, insert, and delete, the time complexity is OM for the average case and the worst case. That's huge. Having that guaranteed performance, that predictable speed, is something that other structures, like hash tables, just can't always promise. It's reliable, and it is wicked fast.
But wait, there's more. Tries are not just for simple lookups in a dictionary. Nope, their amazing structure makes them the perfect launchpad for some seriously powerful pattern-matching algorithms. And one of the coolest is called Aho-Korosik. So let me introduce you to the Aho-Korosik algorithm. What it does is it takes a normal trie, it adds this one really clever twist, and then uses that to find every single occurrence of a whole bunch of patterns inside a big chunk of text. And here's the kicker. It does this in one single pass. One time through the text, no going back, no backtracking. It's incredibly efficient.
So you're probably asking, how does it do that? How does it avoid backtracking? Well, it's thanks to a brilliant little invention called failure links. And I love this analogy. Imagine you put a bunch of invisible springs all over the trie, connecting certain nodes. Now, when you're scanning through text and you hit a character that doesn't match, dead end, you don't have to start all over. Instead, one of those springs, sproing, just pulls you back to the next best possible match, and you just keep moving forward. It's genius. And the result of all those clever little failure links? A search time that is just lightning fast. The complexity is O of n plus z. So n is just the length of the text you're searching, and z is the number of matches you find. That's it. This kind of linear time performance is basically the holy grail of string searching, and it's all thanks to the humble trie. Okay, so this all sounds amazing, right? But it brings up a really important question. When should you actually use a trie? When is it the right tool for the job compared to other data structures? Let's put it in the ring head-to-head with its biggest rival, the hash table. This is the classic showdown, trie versus hash table. Now look, for just a simple, does this exact word exist kind of search, a hash table is usually faster, on average. But, and this is a big but, it has major weaknesses. It can't do prefix searches. No way. You can't ask it to find all words starting with pre, and it can't spit out the words in alphabetical order. A trie, it does both of those things beautifully with that guaranteed O of M speed we talked about. So here's the takeaway. If your problem has anything to do with prefixes or sorting, the trie is your champion, hands down. All right, let's wrap this all up into a quick and dirty cheat sheet, especially if you're prepping for an interview. Number one, you've got to be able to code up the basic insert and search functions. That's table stakes. Number two, know the trie versus hash table comparison inside and out. Know the trade-offs. Three, be ready to explain the big idea behind Aho-Korosik. It's all about those failure links for super fast multi-pattern searching. And finally, number four, be prepared to talk about memory. How you store the child nodes using arrays versus maps has big implications. Get these 4 points down and you'll really understand what makes tries tick. And really, that's the beauty of it. Once you understand a new data structure like this, you start seeing it everywhere. You now know the secret behind autocomplete, spell checkers, and some really advanced search tools. So I'll leave you with this question. Now that you know how they work, what everyday problem could you go out and solve with a trie?